In this lesson, we're going to talk about exponential decay. So exponential decay is a type of exponential function, but it's constantly decreasing. So if you remember thinking about the graph of an exponential decay function, it would look something like this. It would always be decreasing, and it's kind of curved. And when it's decreasing by a certain factor or a certain percent. So we're going to look at today some word problems that use exponential decay. So if we look at this opening exercise here, Malik bought a new car for $15,000. As he drove it off the lot, his best friend Will told him that the car's value just dropped by 15%, and it would continue to depreciate 15% of its current value each year. If the car's value is now $12,750, according to Will, what will be its value after 3 years? So as soon as I read things like dropped by 15% or depreciate 15%, that tells me this is an exponential decay problem. One, decay because of the words depreciate, drop by, but because it's decreasing by a percentage, that tells me exponential. So if we look at this table here, this is talking about the number of years t passed since driving the car off the lot, and then the value after t years. So when t equals 0, the starting value, it's $12,750, because that's like starting right now. It says now, meaning t equals 0. Then after 1 year, it became $10,837.50. So basically what happened is this depreciated 15%. So we took 15% of this, and then we subtracted it off of $12,750 and got $10,837.50. So that's the longer way of figuring it out. The shorter way is to think about, well, if I'm depreciating this 15%, what percentage am I going to be left with of this 12,000? So if you want to know what percentage you're left with, well, take your 100%, subtract off the amount it's depreciating, so 15%. So that means you're going to have 85% of the car's original value left. So let me just write this out so we remember it. So if it depreciates, so remember, depreciate just means decrease, by 15%, that means the car's or its new value is 85% of the old value. So if we're trying to figure this out, I'm looking at to go from 12,000 to 10,000. Well, we know that after a year, there's only 85% of the original left of the previous year if it's depreciating by 15%. So if you want to find 85% of $12,750, what you do is you multiply that by 0.85. So when you do that, you'll get 10,000. So if we do that again, you'll end up with $9,211.86. If you multiply that by 85%, so you want to find 85% of this value, that'll be $7,830.09. So that's how much the car will be left, or how much the car will be worth after it's depreciated from 3 years. 15% depreciation. So that's one way of doing that. Which, could you imagine if you wanted to know how much is a car worth after 20 years? You would have to keep finding all of the previous year's amounts so that you could keep multiplying them by 0.85. So it would take a while, especially when you get to numbers that are huge and you're trying to figure out, okay, what's it worth after 50 years? Something like that. It's going to be a pain because you're going to have to make a table and you're going to have to keep multiplying by that 0.85% every time, and you always have to know the previous year. So to make it shorter for us, what we do is we use these exponential decay formulas. so that if we have a formula and we want to know, say, the 50th year, you plug in 50 into the formula and you got it. You don't have to do 49 other calculations ahead of time. So when we're looking at these kind of problems, there's two formulas that we will think of, because typically you're going to be given a percent, but there could be a time where they say it's going to be half as big. So that means you keep dividing by 2 each time. So that's considered a factor, or it's a third of the amount. You'd be dividing by 3 each time. So instead of having to go through and make a table, we can use these formulas. So if you're given a percent, so like this last problem where it said 15%, the formula that you're going to use will be a function of time. So instead of x, I'm going to put a t there for time, and it's going to be a. So it'll be a times 1 minus r to the t, because remember, this is an exponential function, so that means I have to have whatever my input is. So in this case, this is t instead of x. That's got to be an exponent. Now these other numbers, if you remember from graphing, a is going to be that y-intercept, or that starting amount. So this is going to be your initial amount. R is going to be the decay rate. And it's going to be a percent, but you're going to write it as a decimal. So it's a percent written as decimal. And then t, the whole reason why we're using t is because that's for time. And you could use x if you wanted, but we'll just use t because it makes more sense. So that's when you're given a percent. If you're given a factor, so like I said, like 1/3, 1/2, a fourth, something like that, you're just going to basically use your parent function of what we graphed in the last lesson. So when we're looking at this one, a is still going to be the initial amount. So that's your y-intercept. B, if you remember, is the rate, so that's your growth rate. So for this one, B is going to be, again, that decay rate. But this time it's going to be written as a factor. So if it were a half, you'd put 1/2 in there. A third, you put 1/3 if it's decaying by a third, something like that. So it's going to be that factor goes right in for B, and then T will just be the time again. So really the only difference between these two is right here and right here. So this 1 minus R is really your decay rate, because if you go back up to this problem here, my decay rate, what it was decreasing by, was 15%. But if I want to write an equation, really what it's going to happen is you're going to do 1 minus the 0.15, which is what we did, and we got 0.85, and that's the factor. The 0.85 was what I was multiplying by each time. So this really becomes the factor. But it's just, we talk about it as two separate formulas so that you don't have to think about how to translate it into the factor. You can go right into looking at the word problem and decide, do I use the percent formula, or do I use the factor formula? So let's try some word problems. So the first word problem we're going to try is the same scenario from the opening exercise. The only difference is we're going to look at it using a formula. So for this first one, same scenario. And when we talk about the initial amount and the depreciation amount, the initial amount that we're starting with at year 0, so this is going to be your initial. And then we have the amount that is depreciating. So this is going to mean R is 0.15 because you want to turn it into a decimal, so move the decimal 2 places to the left. So when we go to write our formula, we're going to use the percent formula. So A times 1 minus R to the T. So A is going to be your initial, so 12,750. 1 minus your rate, 0.15, and T is going to stay because it says T years after driving off the lot. We're trying to come up with an equation. So then the only thing I'd recommend doing is just going ahead and simplifying that. We can't combine these because this part in parentheses belongs to that exponent that's being raised to the t, but 12,750 is just getting multiplied, so that's just going to stay out in front. So basically our equation is going to be 12,750 times 0.85 to the t. And if you remember, what I talked about on the last page is that this is in that factor form. This is in the percent formula. This is the factor formula. So the only difference is we actually subtract, and now we got the factor. So the factor of decay is 0.85. So part B is saying use this formula and let's determine the value of Malik's car after 3 years after its purchase. So that means time is going to equal 3. And round your answer to the nearest cent, so 2 decimal places, and then we're going to compare that value. So I'm going to plug 3 in for t, so I'm using this formula here. So we're going to plug in. So in your calculator, you can enter this just as you see it. Just make sure that the 0.85 is the only thing being raised to the third. So you might want to just put that in parentheses. Either that or just do 0.85 to the third first, hit enter, then multiply it. Up to you how you want to do it, but go ahead and try that. And when you do that, see if you get the same thing. So I'm getting $7,830.09 when I round 2 decimal places. And it's asking us to compare that to the table. So if we go back to the table, you should be thinking it's going to be the same value, because how could it not? If it doesn't give us the same value, that tells us our formula is not doing what it should be doing. So if we go back and look at t equals 3, you see that you get the same value. So that's a good thing, because otherwise the formula wouldn't be doing its job. The whole point of the formula is to make our life easier when we got to find t equals 50 or t equals 100, something like that. So are they the same? Yes. They are the same. So then this other question here is asking, okay, after 7 years now. So that means you're going to let t equal 7. So we're going to use the same formula, but we're going to plug in 7. So plug in 7. So instead of t, you're plugging in 7. So when you do that, f of 7, so 7 is the input, you end up with 4,087.36, which makes sense that it's getting smaller. It should be getting smaller, remember, because you're depreciating. So that's that problem. Let's just try a couple more examples just so you get the hang of it. So you could plug in, any number of years. Eventually the car wouldn't have any value. So you would get to a point where you wouldn't end up getting any, it would go, so that there's no value of the car left, and you wouldn't want to keep then plugging in more years, because once it gets to 0, it's done. So looking at the next problem, same idea. So the first thing you always want to decide is it going to be a decay problem? So do you see something about decreasing, depreciating, dropping, decaying, something along those lines, and by a percent or by a factor? When I say a factor, I mean a multiple of something, or a percent. So Kelly's mom takes 400 milligram dose of aspirin at 10 a.m. Each hour, the amount of aspirin in a person's system decreases, so I see decreases by 29%. So this tells me exponential decay because it's decreasing by a percent. We want to know how much aspirin is left in her system at 4 p.m. So initially, here's the initial amount, and she takes 400 milligrams, and that's at 10 a.m. So we want to know, well, how many hours pass from 10 a.m. to 4 p.m.? So from 10 to 4, that means that we have 6 hours that have passed. So this tells me 6 hours between 10 and 4. So we're going to set up our formula. So our formula that we're going to use is the percent formula. So A times 1 minus R to the T. Our initial, we said, was going to be 400. The rate is going to be 0.29 because you're moving that decimal place over 2 places. You can also think of it as dividing by 100 if you're trying to go from a percent to a decimal. So when we actually subtract these, we get 400, and then subtract the inside here, you get 0.71. And then let's actually go ahead and plug in this 6 hours. So we're trying to find how much is left after 6 hours, so the time is 6. So I end up with 51.2 milligrams. And it doesn't say what to round to, so I'm just going to do one decimal place for this. So 51.2 milligrams is what's approximately left in our system after 6 hours. So the last example we're going to look at together is example 3. So for this one, each year the local country club sponsors a tennis tournament. Play starts with 128 participants, so that means we're starting. So my initial here is 128. During each round, half of the players are eliminated. So eliminated tells me decay, half tells me the factor. So this is going to be a factor one. So the factor, or the decay factor, is going to be 1/2. So the formula we're going to use, keep blocking out that screen on you. So the factor we're going to use is going to be f of t, or the formula we're going to use, f of t equals a times b to the t. We're going to use that formula for this one. So our initial rate is going to be 128. The decay factor is 1/2, so I just plug in the 1/2 to the t. So here's the equation. The second part says how many players remain after 5 rounds. So this means that t equals 5. So let's go ahead and plug that in. So when you do that, you end up with 4. So 4 players. There's 4 players left after the 5 rounds, of half are eliminated, and you start with 128. And then this next question is kind of a follow-up question to this. So how many rounds of play will it take to determine a champion tennis player? So for this one, we're not trying to find how many players are left. We want to know how many rounds. So this means we want to find the time, because time in this case is our rounds. So in order to do this, think about what it means. If there's a champion left, or if there's a champion tennis player, if we determine a champion tennis player, that means only one player would remain. So only one player remains. So that means if I'm using this equation from up top here, this means that f of t has to equal 1. The equation has to be set equal to 1 because when you're solving f of t, the y value, or the output, stands for the number of players. So that has to be set equal to 1 this time, and we're going to solve for t. So what it looks like is, instead of f of t, it's going to be 1 equals 128 times 1/2 raised to the t. So we're trying to solve this. We need to find how many rounds until this whole thing equals 1. So you could do this by guess and check, so just plug in some different numbers. Obviously you would want to pick numbers bigger than 5 because you know after 5 rounds there's only 4 players. That's one way. The other way is to use your use your calculator and graph it. So what you're going to do in your calculator is you're going to put this into f1 of x, and then put this into f2. So you're going to treat this as two separate equations. So you're going to have f1 of x equals 1, f2 of x equals 128 times 1/2 raised to the t. And then you're going to end up with a graph. So go ahead and enter those. You should see something. So basically you're going to have f of 1 equals f1 of x equals 1. That's going to be a horizontal line going through 1. So y equals 1. Let me label x and y axes here. So when you graph this, you should end up with a horizontal line. And then your second equation, so this equation, you should see something like this. So this would be the second part. So this would be y equals 128 times 1/2 raised to the t. So this is the first part. First graph, second graph, you want to find, well, when are these things equal? So when they're equal is this point right here. So when you enter these into your calculator, if you just go to Zoom Standard, so if you go to Menu and then go down to the window and then just pick the standard one, you should be able to see it. So if your graph you can't see the intersection, just do Zoom Standard and it'll fit. And then what you're going to do is you're going to go to Menu, Analyze Graph, and you're going to use the intersection feature. So in your calculator, Menu, Analyze Graph, and then intersection. And then from there, remember, you have to take those little bars and you have to slide so you're shaded over the intersection region. So your calculator will allow you to slide. And then you get this part shaded. And then it'll tell you that this point is 7, 1. So the solution to this, when they're equal, is at t equals 7. Because remember that the t is the x value and the y is the 1. Or that's the number of players. So the solution then for this is 7, 1, and 7 stands for the time or the number of rounds. So this is our time, and then remember the 1 is the y value, so in this case y stands for how many players are left. So this is your output value, or f of t. So what that means is after 7 rounds, there would be only 1 player left. So after 7 rounds, 1 player would remain. So a champion is determined. Was determined. So that's it then for that video. And then we're gonna do some more practice with exponential decay and then start talking about exponential growth within word problems.